Hello YouTube, and thank you for watching. This is a continuation from previous session which covered what an index is, how the index improves the query, and measure the query improvement. We will dive into a more technical discussion using this student table, which consists of 6 columns and 5 rows. This query is looking for all records where total equals 150, which returns one row. Let's take a look at the execution plan. The execution plan shows that the query performed a table access full or table scan, where basically it scanned from left to right, top to bottom. The CPU cost is 3. The number of buffers read is 7. We will be using this to compare query improvement. As I mentioned previously, an index is a copy of the column that has been sorted. So we will create an index on the total column to satisfy the query. Let's go ahead and rerun the query again. Now, rather than doing the table scan, we will be using the index, which will significantly reduce the query execution time and the number of buffers. Let's look at the execution plan again. So previously it was doing a table access full. Now it's doing an index range scan using the index that was just created. The CPU cost has reduced from 3 to 1. The number of rows remain the same. The runtime is reduced, though it is not reflected here because it's very small. The number of buffers has been reduced from 7 to 1. Let's move on to compound index. We'll use this query as an example, which will fetch records where total equals 145 and subject equals 68. Let's go ahead and execute this query. It returns one record. Let's take a look at the execution plan. The query is using the index that was created on the total column. The cost is 2. Number of rows fetched is 1. And the number of buffers read is 2. One way that you can improve this query is to create an index on the other column, the subject B. Interestingly, the query decides to use the index on the total column rather than on the subject B column. I'll explain why this is the case. When a query decides to use an index, it looks for what's called selectivity. Another way to say it would be uniqueness. So we have two columns here, total column and the subject B column. What you'll notice is that total column has 5 unique values. It has high selectivity. Subject B column has 3 unique values. There's 68, 75, and 77. So the total column has 5 distinct values, whereas the subject B column only has 3. So when a query looks at these column statistics, it will choose the index that has the higher selectivity or higher uniqueness. This is the reason why the query is using the index of the total column. Now let's look at the composite index, and what we'll do is run this query again. So currently it is using an index that's on the total column, but the query is searching for 2 filters, one on the total and one on the subject B. So to help the query performance, we can create a composite index on the 2 columns. The way to decide which column is the leading column is to look at the column selectivity. And since the total has the higher selectivity, it should be the leading column. So here we have composite index, which consists of the total and the subject B, and total is the leading column. Okay, let's go ahead and re-execute this query and look at the execution plan again. As expected, it is now using the composite index. And let's compare the query improvement. The cost has remained the same. The number of buffers has remained the same. The reason for this is because the example data is too small. In real world, you're dealing with hundreds of millions of records, and the cost savings and the execution time would be significantly reduced. In this example, it's very difficult to tell the difference. But at least we've proven that the query will use the composite index over a single column index. One of the more common questions that students ask is, what is the difference between having the leading column total versus leading column subject B? As I mentioned earlier, when the database is looking at indexes, it selects based on higher selectivity. So total column has 5 distinct values, subject B has 3. And with this example, it's a ratio of 5 to 3. In a real-world environment where you're dealing with hundreds of millions of rows, this can vary significantly. For example, this could be in the 10,000 range, and this could be in the 1,000 distinct value. And therefore, the query improvement improves drastically, depending on whether you are putting the total as a lead column or the subject B as a lead column. Let's go ahead and create the index with subject B as the leading column. And then let's rerun the query one more time. And let's see what the optimizer is using. So in this case, the optimizer decides to use a new index with the subject B as the leading column. In this example, with a small number of data sets, it really makes no difference. And so the optimizer can choose either one, and the query has not improved at all. But in the real world, this would make a significant difference in terms of runtime, in terms of CPU cost, in terms of buffers. I hope you found this information useful. If you like the content, please hit the like button and subscribe. Thank you.